Welcome learners to this session of course on material science. I am Dr. Shashank Shrivastava from School of Engineering and Technology, Indira Gandhi National Open University. So in this session, we will be covering about the brittle fracture of the ductile materials due to service conditions, then the toughness, what is the toughness and how toughness is affected by our different temperatures, how toughness is affected by the temperature range, and we will also discuss about how this toughness test is carried out. So let's start with this brittle fracture dependent on the service conditions. So we see that crack propagates suddenly without any plastic deformation and producing loud report due to sudden release of strain energy. So crack, actually very small crack, can also propagate at a very fast rate and under certain conditions. Now I will tell you a story regarding this, which is very famous. The story about the Titanic, the ship which its builders said that the persons who built it, that even God cannot sink it. But it sank in the very first session. So two lessons we learned from that don't challenge God, and the other one is about the materials and the temperatures effect and whatever else was there. So whole study was done after that. And it came out that what happened with the Titanic actually, that it was a region of very low temperature where the ship was going. So although very perfect type of materials like stainless steel and whatever was available at that time, they were used in the making of that ship. But what happened that due to the temperature, very low temperature, they got brittle at that time and they broke suddenly. When it collided with that ice, the glacier, it broke up. It turned into brittle material instead of being ductile. So such type of disasters can happen due to this material failure, and that's why this material science is so important. So now move forward. Fracture tendency in a material like a steel develops because there are three main reasons. First one is the triaxial state of stress. The second one is the low temperature, as I told you. The third one is the high strain rate or the rapid rate of cooling. So the stress, it is acting in three directions. It is triaxial. So it's very complicated actually. Then the temperature, and finally the strain rate, as we have discussed in the previous session also. This strain rate is also very important. What is important then in this? Toughness is very important. There is one property which is called toughness. So the combined effect of triaxial state of stress, such as in a notch, if there is a notch in a material, suppose in a specimen, there is a crack, a small crack like I discussed earlier, and it can propagate very fast. So we have to see that it stops, the propagation stops. So what to do then? So for that purpose we are discussing this. So complicacy of the triaxial stress, low temperature, and that is accentuated by high strain rate. So all these three things have to be discussed together in combined way. Thus laboratory tests with all these three service conditions need to be performed to determine tendency of a material to fail in brittle manner. So even a ductile material can fail in a brittle way depending upon the service condition. So what to do now? We have to resort to impact test. So for this purpose now we discuss the notched bar impact test. To determine the tendency of material to fracture in brittle manner, generally most tests are performed on bar specimens which carry notches in most critically stressed zone under impact, and the strain rate here is 1000 per second. As I discussed earlier, the impact load begins from 10 per second, so it goes up to any number after that, like here it is mentioned 1000 per second. Carrying out the impact tests on notched bar samples at low temperatures renders most severe conditions which might exist in service. So there are certain difficulties in static tests actually. Why we are performing this notched impact test? We are performing this because the other tests like the simple tension test and simple compression test will not give us anything about our toughness of the material. So the problem there is that stress calculation at the tip of the notch under impact load is very difficult because of the triaxial state of stress that exists around the notch tip under a static load. and it is modified considerably under the impact load. So we cannot exactly determine the triaxial state of stress. Then the other reason is that the relative magnitudes of the stress components at notch tip depend upon the dimension of the notch and the specimen. So magnitudes of stress are depending on the dimension of notch and specimen. If we keep on changing that notch size and dimensions, then this magnitude of stress will also change. So it becomes very difficult to calculate this kind of stress. So we see that stress measurement being very difficult. Now what we have to do? We have to resort to energy absorption type of tests. We will make energy absorption as the measurement criteria for impact toughness. Notch is made of standard dimensions. As I mentioned earlier, if notch size or dimension vary, then the test becomes very difficult. So it's important that notch should be of a standard dimension and the procedure should be standardized. Impact toughness cannot be generalized for a material, but is a property of the specimen of a material. So we have to understand this thing, that toughness is as such not a material property because it is dependent upon the specimen. So this property of impact toughness, it is a good qualitative index of behavior of material in presence of notch and at low temperature. So as I discussed earlier, if we want to know about the failure of a material under different service conditions, so the best test in that case is this notch. Hence this property of material is used in selection of material and for development of material for specific purposes of inhibiting the tendency of brittle fracture. So whenever we want to know about the brittle fracture tendency of any material, then we have to resort to this impact toughness test, and particularly in case of steel. So now we begin this impact test. How is it performed? What its name is? So it is first one is named as CHARPY impact test procedure. So here is the machine also shown in the figure. The CHARPY impact test, actually it is named after the scientist who discovered it, and it is performed on a square cross-section specimen. The specimen on which the test will be performed will be of a square cross-section, and it will have a notch on one side in the central cross-section. So if there is a suppose square type section, there will be a notch on one side of the specimen. On the other side it will be plain. The specimen is placed in CHARPY impact testing machine. This square type cross-section specimen is placed in the machine at one point and it is simply supported. Further what will happen? There is a swinging type of pendulum. This pendulum will hit the specimen or strike the specimen at the central cross-section but on the opposite side of the notch. So here is the specimen. You can see here, it will be more clear to you. It is a rectangular type of piece, but its cross-section is square, as I told you earlier. Its cross-section is square. So in the figure you can see here, we use a standardized type of component. So here are the details. Commonly used impact specimen, it is 10 mm square cross-section beam of 55 mm length. So its length is 55 mm, the cross-section is of 10 mm, and it is supported over 40 mm span, as you can see in the figure, and it is a V notch on one side in the central portion, and its angle is 45 degree, depth is 2 mm, and root radius is 0.25 mm. So this is a standard specimen. Now we discuss about the machine. The machine, it consists of a rigid and a strong structure of two columns on a heavy base. You can see from the figure there are two columns. One is this one and the other one at the other end. So these are the two columns, and the columns, they carry a heavy swinging pendulum at their top. There is a pin. The pin is connecting the two columns, and on this pin you can see in the figure that this pendulum is attached at the top, and this pendulum swings on this frictionless pin, because if friction is there, energy loss will be there. So we try to keep it as much friction free as possible, and this whole thing actually is supported on a platform at the bottom. See here, these two columns are supported at the bottom on a platform. The striking edge should be in level with the central cross section of the specimen when the pendulum is in vertical position. So the striking striking portion should be exactly matching with the center of the specimen, and the mass of the striker or the hammer is concentrated in vertical plane. It is very important because if it is not in vertical plane, then breaking the specimen would be difficult or rupturing it would be difficult. I will also show you in demonstration number 2. A circular disc scale mounted centric with the pin of the pendulum reads this position. So here is the circular disc. It's a kind of a scale and it is mounted on the pin of the pendulum, which I showed you earlier. So it reads this position, but it is often calibrated in terms of the potential energy of the pendulum. It is not that it is according to the position of the pendulum, which is moving from the topmost position and going to the bottom and then moving to the other side, but it is with respect to the energy, potential energy. So now we discuss the test procedure. What happens in this CHARPY test? We have discussed about the machine and whatever are the components in this machine. So now we discuss the test procedure. So centering device is used. There's a centering device which is used to place the specimen at the center of the machine between the two columns. So between the two columns the specimen is placed, and with the help of the centering device it is exactly placed at the center. The pendulum is raised to and held at its extreme position. So this pendulum is raised to the extreme position. Here it is given in the figure also, and after positioning it like that, we release it. It is allowed to fall. So at its extreme position, if you say that it is at a height of h1, we can say that it is at a height of h1 from the specimen, vertical height. Then the pendulum will have potential energy WH1 at the extreme position. W is the weight of the pendulum in this expression. So in this position, the arm of the disc scale is in its extreme position. The scale which I told you earlier, so there is an arm in that pointer which is at its extreme position, and it reads total amount of energy is stored in the hammer. So now we have got the energy. WH1 is the potential energy. So when it is released and it reaches at the bottom and it strikes the specimen, it is said that it reaches with a velocity of 4.8 meter per second. That means the height at which the pendulum was at its extreme position is round about 3 to 3.5 feet. Under this condition, the specimen is forced to bend with a rate of 10 to the power of 3 per second. So it's quite a high strain rate, you can see, and it's an impact load, and it results into instantaneous fracture or plastic deformation. The pendulum continues its swing after fracturing or deforming the specimen and rises to a height of h2. So the first height it was h1. Now it has lost certain amount of energy, so it is going on the other side only up to a height of h2. So thereafter the pendulum will swing back, because a pendulum has to and fro motion, oscillatory motion. So it will keep on swinging till its energy completely dies down. But with the scale, the pointer on the scale will not move back, because it is fixed with respect to the potential energy. So the position of the dead pointer reads the difference of potential energies of the pendulum in two extreme positions. And what are those positions? The first one was corresponding to h1 and the other one is corresponding to h2, as I told earlier also. So naturally this difference of the energy is that which was absorbed in fracturing the specimen. So if we want to devise a formula, it will be given like, suppose UF denotes the impact toughness, so it will be given by W into H1 minus H2. But there may be one more problem, that is that energy loss may be there in the bearings of the pendulum and due to air resistance also. So we know that there is air drag, so both things need to be accounted for. So these losses may be determined by a simple experiment in which the pendulum is allowed to fall from its extreme position without placing the specimen in its path. So what happens with this experiment now? The other extreme position to which pendulum rises now will be slightly lower than its initial position. That means that it will be lower than H1, but it will be higher than H2, because the energy loss is less as compared to when the specimen was placed. And the difference of the potential energies in two positions indicated by the position of the dead pointer is the loss of energy to bearing friction and air resistance. Now we have got the energy loss due to the bearing friction and the air resistance. So the final thing that comes out, the energy loss has to be subtracted. UL has to be subtracted from UF, which we got earlier, and the formula will slightly change and it will become like this: WH1 minus WH2 minus UL, and we have got the correctness or the correct value of impact toughness by reducing or subtracting the bearing loss and the air drag. So after discussing the first kind of impact toughness test, that is the CHARPY test, now we discuss the second type of test, that is the IZOD test. There's one more test. So this was discovered by IZOD, so it is named like that. IZOD impact test specimen, it is shown in the figure, is either circular or square in cross section. Earlier in case of CHARPY we saw it was only square cross section, but in case of IZOD we can use both circular as well as square, and it has also got a V notch at one end like given in the figure. The specimen is clamped at notched end in vertical plane as cantilever beam. So here the position of the specimen is also different with respect to the CHARPY one. There the specimen was placed in a horizontal manner. Here it is placed in a vertical manner, you can see from the figure. And the swinging hammer strikes the free end at a distance of 22 mm from the notch. So the notch is at a distance of 22 mm from one. This is standard condition. So the mass of hammer in case of the IZOD machine is distributed in the horizontal plane. Obviously, like we discussed in case of the CHARPY, it was in the vertical plane. Here it is different because we have to break the notch from a different direction. So it has to be in the horizontal plane. Nowadays what is happening is the same hammer is being used in both the machines with attachable strikers for CHARPY as well as IZOD. So the difference between the CHARPY and the IZOD we can see here. In case of the CHARPY, the specimen is simply supported in horizontal plane, whereas in case of the IZOD test, the specimen is like a cantilever in the vertical plane. Second difference, mass in case of CHARPY is concentrated in the vertical plane, whereas in case of the IZOD test, mass is concentrated in the horizontal plane. Okay, after discussing about the CHARPY and the IZOD test, let's discuss about the temperature effects on these tests. So we know that our surroundings temperature does vary according to time and place and has a profound effect on the properties of various metals and alloys, especially steel. Like earlier I gave you the example of the Titanic ship. So that's the same case. Now we discuss about the low temperature effects. Impact test experiment at different temperatures is very much needed because of the temperature effects. And it has been seen that steel is very much affected by low temperature. So here is one figure which gives us the impact toughness versus the temperature. It is that graph, impact toughness versus the temperature. And there are two kinds of steel A and steel B. The steel A, it shows a sharp transition from ductile to brittle in the temperature range of 0 to -20, as you can see in the figure here. If you see the A1 in the range of 0 to -20, the slope of this line is quite high. So the temperature range, this temperature range where this transition is taking place from the ductile material to brittle material is known as the transition range. So the transition in fracture mode under impact loading has been described here. And this temperature, like I described the temperature range, this temperature also, it is known as ductility transition temperature. A lower transition temperature is desirable in practice because then the brittle fracture shall not occur in service temperature range. Why is it said so? See, if we keep on decreasing this side temperature, if we go towards the left side in the graph on the temperature scale, then we can see from -20 to -40, further -60. So if this temperature goes on decreasing, then we will never come to this point actually, and no fracture will take place. So that's why it is said that lower transition temperature is required. Like we discussed earlier about the CHARPY and IZOD test, but if they are performed at room temperature, it is not of very much value as such, because from the graph you can see, if you see the steel B, so steel B in comparison to the steel A has lower impact toughness at room temperature, but when we go in the range of 0 to -20 degree, then steel B is very much better because there is no sharp decline from ductile to brittle material. So low temperature impact test or room temperature impact test doesn't give us too much of results. Thus, to understand the material tendency to behave in a brittle manner, it is essential to determine the ductile to brittle transition range in terms of temperature. So after discussing the low temperature effects, let's discuss about the high temperature effects. High temperature also has quite a lot of effect on steel material. So there are two distinct properties in this case, yield strength and the fracture strength, like we have seen in the stress strain diagram also. So both of these properties decrease with increasing temperature, reducing strain rate and triaxiality. So if we increase the temperature, the yield strength also decreases and the fracture strength also decreases. But what happens is that in the figure you can see here that the reduction of the yield strength, if you see here, the reduction of the yield strength is much faster than the reduction in the fracture strength, much faster, because the slope you can see in the curve is much faster. So what will happen due to this, that both the curves, one of the yield strength and the other one of the fracture strength, they will intersect at some point. And this is given here in the figure. Then a dotted line is drawn up to the horizontal axis. It is known as CA. So this is the line of the transition. So as a result of that reduction in fracture and yield strength and the different slopes, the yield strength, which was initially higher, becomes lower at the point of intersection. So you can see the portion that is rightwards of CA. So here you can see that the yield strength has gone down with respect to the fracture strength. Whereas if you see the left hand side of CA, then the yield strength is higher than that of the fracture strength. So what will happen due to this? What will be the consequence actually? So if a specimen loaded on the right hand side of ordinate CA, then it reaches yield stress first and will plastically deform. So it will not break, instead it will deform. Whereas if the loading is on the left hand side of CA, then what will be the result? Then fracture will reach first and there will be a brittle fracture. So after discussing all these things, what are the temperature effects, the low temperature effect and the high temperature effect, let's see how the microscopic changes are there in our specimen. A brittle fracture as below temperature TR, that was the transition temperature, exhibits a granular surface, like you can see here in the figure. The granular surface is there in case of the brittle material, which is characteristic of cleavage fracture and absence of any shear deformation. So there will not be any shear, but there will be granular type of thing. As the temperature rises, the part of the notch section, the region near the surface, tends to fracture in shear mode. Now if the temperature is rising, then what will happen? There will be a tendency of shear, whereby energy absorption in fracture increases. This shear deformation results in transverse contraction of notch section, and the percent contraction is sometimes reported to indicate the ductility of the material. So it is said that ductility of the material depends on the percentage contraction of the notch. Like the first figure you see on the left hand side, it was about brittle fracture. As soon as the temperature is increased, a certain notch contraction is taking place, but still the fibrous material is there. The fracture surface on which failure occurs due to shear is marked by fibrous appearance and considerably transverse contraction in the notch section. Like I told you, there will be fibrous appearance, but in addition to that, there will be contraction also in the notch. And finally, what will happen? This notch will become bigger, and it is given by the dimension D when it has completely reached to the fracture part. So there are certain other factors also in addition to the temperature effects and the strain rate effect. There are miscellaneous factors also which impact the toughness. The first one is the machine itself, the CHARPY and the IZOD machine. So each machine will absorb some energy when the specimen is struck by pendulum, and this amount, though very small, will vary from machine to machine, and thus the impact toughness will be affected. And the second thing is the notch root radius. So the notch root radius has to be standardized, and any deviation from it will influence the result. A sharper radius will tend to reduce the impact toughness, while a coarser radius will increase the amount of energy absorbed during fracture. So these are some of the metallurgical factors which will be affecting the impact toughness, like we are adding certain amounts of other elements, alloying, So in case of carbon, we see that each 0.1% increase in carbon percentage raises the ductility transition temperature by about 14 degrees centigrade. Manganese, each 0.1% addition of manganese in steel reduces the transition temperature by about 5 degrees centigrade. So what is happening here, you see, like I had told earlier, the transition range was there and the CA line was in the curve. You can see that curve and you can get to know how it is changing, what I am describing here. So phosphorus addition, it also raises transition temperature. Nickel addition, beneficial effect on notch impact property. So if we add nickel to the already existing element steel, then it will be beneficial. Chromium, there it has no effect. Silicon, more than 0.25% addition of silicon raises transition temperature. Nitrogen, it is very hard to detect the influence of this, but it is said that because of interaction with other elements, it is considered detrimental. Molybdenum, it increases ductility transition temperature similar to carbon. And oxygen, it raises transition temperature in the higher temperature range. Then grain size and specimen geometry also affect the impact toughness. How does the grain size affect? So it is generally seen that the transition temperature reduces with decreasing grain size. This effect is observed both in mild steel and higher alloyed steel. Similarly, in thick hot rolled plates, it is not possible to obtain uniform fine grain size throughout the thickness. So the transition temperature will be appreciably higher. Also, a specimen of varying geometrical factors affect the loss of fracture energy. It is very well known that finding a weaker point in a large specimen is more difficult than finding it in a small specimen. So now in this section we discussed about how the different kinds of material may fail in a brittle manner due to different service conditions, like the different strain rate effects, the low temperature effects, and triaxial stress effects. All these we discussed, and we also discussed about the CHARPY impact test and the IZOD impact test. They were very important because they let us to know about the toughness which is important in these service conditions. So all this we have discussed, and further we will see in the next lectures. Thank you very much.